Shall we start? Great. Oh, okay. So our next speaker is Xuanqiang Zhao. He will tell us about information recoverability of noisy quantum states. Please.
Thank you for the introduction. Hello, everyone. I'm Xuanqiang Zhao. Today, I want to share with you this work titled as Information Recoverability of Noisy Quantum States. This is a joint work with Zhao, Zihan, and Xinwang. And it was done when I was a research intern at the Institute for Quantum Computing at Baidu Research. The information we refer to here in the title is the shadow information. We know that quantum states are the carriers of information in quantum computing. It not only carries quantum information, but also classical information. And the results we usually want from quantum computing are still classical, like the measurement results of some quantum systems. So shadow information is one kind of classical information. That is the expectation value of some chosen observable. We call it shadow information because you can imagine the quantum states as a 3D objects in the space, like the cone shown here. So if you observe it from top, you will see a triangular shadow. And if you observe it from the left, you will see a circular shadow. So different observations, different observables will give us different shadow information, which corresponds to the different shapes of shadow here. And it is important because the shadow information is target of many quantum algorithms. For example, the variational quantum eigensolver for the chemistry simulation and the algorithms for solving nonlinear differential equations. And both of them can be run on near-term quantum computers. The near-term quantum computers are prone to noise. It results from that the quantum system usually suffer from unwanted interactions with the environment. For example, energy could flow from the quantum system to the environment, which is called energy dissipation. So such noises can be modeled as quantum channels, which are completely positive and trace preserving maps, or just CPTP maps. And each quantum channel has a cross representation, which is as shown in the blue box. So the operators EK are the cross operators for the quantum channel, and they satisfy this completeness condition. As example, here are the cross operators for the amplitude damping channel, which describes the process of energy dissipation. So we know that during the process of computation, the noise can affect the states of the quantum systems. For example, the coin showing on the left are transformed into a cylinder on the right. And it will also change the shadow information encoding in the states. So if we observe the both objects from the top, we will see totally different shapes of shadows. This means that undesirable quantum channels will corrupt the shadow information and yielding misleading results. On the other hand, if we observe both objects from the left, we will see the same circular shadow. So this tells us that what observable we are using to measure matters. So this example raises the first question we study in our work, that is, when is the shadow information with respect to an observable preserved? To approach this question, we consider from an operational perspective. In particular, we consider the optional task of recovering the faithful shadow information from the noisy quantum states. And we consider within this probabilistic sampling framework. So at first, we have multiple copies of the noisy quantum states. For each copy, we apply a channel sampled from a set of channels, and then measure the states in the basis of the observable of interest. After getting all the measurement results for all the copies, we will post-process to estimate the noiseless shadow information. We use this framework because it combines the general quantum operations and memory efficient way to manipulate quantum states, because we only need to do local quantum operations rather than global ones. And similarly, frameworks have been used in predicting properties of quantum states, as well as mitigating quantum errors. So far, we have covered the problem of preservativity into a problem of recoverability. And for a piece of shadow information to be recoverable, we mean that there exists such a map D, which is linear combination of the quantum channels, such that when we apply this map D to the noisy quantum states and measure the new state with the observable O, this should give us the same shadowing information as we measure the noiseless state in the original case. And if we take the map D here, we call it as a retriever because it retrieved the shadow information we want. And this is described by a permission preserving and a trace scaling map. So by trace scaling, we mean that this map scales the trace of the input operator. Okay, so if we use the adjoint maps of the map D and the channel N, we can rewrite this equation into this form, in the form equation shown below. So if we want this equation to hold for an arbitrary quantum state rho, then we observe that the two parts highlighted in the orange boxes should be equal. So now we arrive at a minimum requirement for a piece of shadow information to be recoverable or equivalently to be preserved. That is, the N dagger D dagger O should be equal to O. So now the question is to ask, when does there exist such a retriever D such that the minimum requirement is satisfied? We first know that if the requirement holds, then the observable O must be in the image of N dagger, because we can see the D dagger O as a whole and as the input to the map N dagger. And then the observable O is just the output of it. So O is in the image of N dagger. Now the question is the converse statement also true? The converse statements say that for any observable O in the image of the adjoint map of the noise channel, there exists an Hermitian preserving and trace scaling map such that the N dagger D dagger O equals O. So the main technical difficulty is the trace scaling requirement on the retriever D. And our main results show that this converse statement is also true. So the answer is yes, the converse is true. And this forms a necessary and sufficient condition for a piece of shadow information to be recoverable. That is, the observable O is in the image of the observable space under the adjoint map and dagger. So this provides a full characterization of the range of recoverable shadow information. Now please allow me to illustrate this condition a bit more. So at the beginning, we have the noiseless quantum state rho. And for any observable in the whole observable space, we can retrieve its shadow information. Now if some noise channels corrupts the states into a noisy quantum states, then for those observable in this brown area, we can still retrieve their shadow information with the help of a retriever D. And the brown area is just the original observable space evolved under this evolution of the N dagger. Moreover, for any observable outside of this brown area, we cannot retrieve their shadow information. So this is a necessary and sufficient condition for the recoverability of shadow information. And the proof to this condition has two parts. The easy part is the necessity part. That is, if the minimum requirement is satisfied, then the O is in the image of N dagger. This is because the map D dagger is still Hermitian preserving, so the D dagger O is we can denote D dagger O by the observable Q. And so O is just the image of the observable Q under the map N dagger. The hard part is the sufficiency part. We need to prove that if the observable is in the image of N dagger, then there must exist Hermitian preserving and trace scaling map D such that this requirement holds. And we suppose that there exists a operator Q that evolves into the operator O under the evolution of map N dagger. And we construct the retriever D such that the D dagger maps the observable O back to the observable Q. To ensure that D-dagger is tree scaling, we split the observable O into 3 cases. So in case one, we have the not fully ranked and not traceless observables. And we use techniques like space segmentation and unit scaling to ensure that the map D is tree scaling. For case 2 and case 3, we did some manipulation to reduce them into case 1 so that we can use the map we construct there. So this completes the proof of the sufficiency part. And in the end, the sufficiency part, what we really prove is that for any 2 observables, there exists a HPTS map such that maps one observable to the other. And so now we have the condition for the recoverability of shadow information. And we know that different quantum channels could have different level of the shadow information preservativity. For example, the quantum channel N1 here, it only crops 1 dimension of the shadow information, because if we observe it from the left, we will see the same shape of shadow. There could also be another quantum channel N2, such that it crops both directions, both shadows from both directions. So now the question we consider is how to quantify this level of shadow information preservation by a quantum channel. And we propose a quantity called the effective shadow dimension. This directly follows from the necessary and sufficient condition we just mentioned. And it's defined as the dimension of the observable space evolved under N-dagger. So it's the just dimension of this brown area. So remember that if and only if the shadow information can be recovered, if and only if the corresponding observables are in this brown area. So we just take the dimension of this area of this space as the effective shadow dimension. And this quantity is easily computable by using the channel's cross operator. So we first use its cross operator to calculate the channel's matrix representation. Then the rank of this matrix representation is the effective shadow dimension. So now we are giving the operational meaning for the rank of a channel's matrix representation. And based on this effective shadow dimension, we further define a measure called shadow destructivity to measure channel's ability to destroy shadow information. It is defined as the log of the d squared over the effective shadow dimension. So d squared is the dimension of the original observable space. We take the log of this ratio so that the shadow destructivity has some meaningful properties. For one, it is faithful in the sense that shadow destructivity is non-negative, and it achieves 0 if and only if all shadow information can be recovered. It also satisfies additivity. Consider that we have different quantum channels acting on different subsystems. Then the global shadow destructivity is just the sum of local ones. Also, shadow destructivity satisfies data processing inequality, which tells us that if we send the quantum states through more quantum channels, the destruction to the state's shadow information will only become worse. So that's the 3 properties of the shadow destructivity. And now that's for the recoverability part where we have a full characterization of the range of recoverable shadow information. And to retrieve a certain piece of shadow information, there is some cost. And now we consider the question of how to quantify the cost of recovering a piece of shadow information. So recall that our retrieving protocol is a probabilistic sampling protocol. It uses many copies of the noisy quantum states. So it's reasonable to take the number of copies required as a measure for the cost. So let's first review the retrieving protocol. So given S copies of the noisy quantum states, for each copy, we apply a quantum channel sampled from the decompositions of this retriever D. And then we measure in the basis of the observable of interest and get a measurement result O. After obtaining all the measurement results, we do a post-processing to arrive at the estimator for the original faithful shadow information. If we further assume that the measurement result O lies within the interval from -1 to +1, then by halving the inequality, the probability of the estimation within a certain error epsilon satisfies this inequality. So on the left-hand side, we have the probability that the estimation has an error larger than we expect. And on the right-hand side, we have bound to that probability. So by some simple derivations, we will have this formula for the number of copies required if we want to have a certain accuracy of the estimation. It's interesting to note that this number of quantum states required is proportional to gamma squared, where gamma is the sum of absolute values of the coefficients in the decomposition of the retriever. So we can use gamma as a measure for the cost of retrieving a shadow information. And even if we have the information on the quantum channel and an observable O, the values of gamma can vary. So there are two important factors that affect the values of gamma. First is that a retriever D has different decompositions, and different decompositions will lead to different values of gamma. So it is desirable to find a decomposition of the retriever to obtain a minimum gamma, and we denote this minimum gamma as gamma minimum of the retriever. Another factor is that there could be multiple retrievers that is valid for retrieving the shadow information. And it is also desirable to find a retriever with the minimum gamma minimum. So combining these two factors, we define the retrieving cost of a quantum channel with respect to an observable as the coefficient gamma minimized over all the valid retriever D and all their valid decompositions. And this cost is efficiently computable with semi-definite programming. And the semi-definite programming will also give us the optimal retrieving protocol corresponding to this retrieving cost. So now we present a case study with the generalized amplitude damping channel. So a GAD channel describes the process of energy dissipation at a finite temperature, and it has these 4 cross operators. And the task we consider is to recover the shadow information corresponding to the poly X operator from the states corrupted by GAD channels. One can adopt conventional error mitigation methods, which implements the retriever D as the inverse of the quantum channel. But it does not exploit the information about the observable we have. Our method gives the optimal protocol because it employs an observable adaptive strategy. So it uses the information that we are measuring a poly X operator. And as shown on the right hand, there is a figure compares the cost of our method and the conventional error mitigation method. So it shows that our method consistently achieves a lower cost than the conventional method. It implies that our method could be potentially used as an error mitigation method to suppress noise that's common on the near-term quantum devices, and it achieves an optimal cost. Another advantage of our method is that it extends the scope of application of a conventional error mitigation method. So conventional error mitigation method only works for the case where noise is invertible. However, our method could also work in cases where noise is non-invertible as long as the as the necessary and sufficient condition is satisfied. So to summarize our results, we address the problem of shadow information recoverability by introducing a probabilistic sampling framework for the retrieving shadow information. Within this framework, we arrive at a necessary and sufficient condition for a piece of shadow information to be preserved or equivalently to be recoverable. And based on this condition, we propose a natural, easily computable measure, which is the shadow destructivity for the destruction of shadow information. And it has some meaningful properties. Then we define a measure called retrieving cost to measure the cost of recovering a certain piece of shadow information. It is efficiently computable with semi-definite programming, and the semi-definite programming will also give us the corresponding optimal protocol. For future studies, we think it would be interesting to consider how to combine our results with error correction or error mitigation so that it can be used in practical scenario. Also, we can consider the cases where we don't have the complete information of the noise model, which is usually the case in practice. And lastly, we can consider the connections of our results to the quantum capacity, which measures a quantum channel's utility to transfer a certain type of information. So that's what I want to share with you today. Thank you for your attention.
Okay, thank you very much for the great talk. We again have plenty of time for questions.
I have a question.
Go ahead.
Can you hear me? Could you go back to the background slide? In the background slide, you had images of number 6 there. That'll do. Actually, go down to 7 if you would. Now you're talking about shadow information, and where you're looking at the observables and the shadows that it casts based off of the the state tomography that you have there, I assume, which is inside the cone. Is there a relationship between the shadow information and the classical shadows? I noticed that you had referenced Huang et al., 2020's paper on classical shadows. So is there some, but that, to my understanding, classical shadows is a sampling done randomly throughout the state tomography. So is there a relationship between the shadow information here and classical shadows of the, Huang et al. Has been working on?
Yes, I think the classical shadows, it consists of like a set of the shadow information, right? So like you are using maybe the set of Pauli operators to extract the classical shadows from the quantum states. And you will need to use many Pauli operators and do many measurements so you can get a classic shadow of the quantum state. And here for the shadow information, we just mean a piece of shadow information is just the one expectation value corresponding to one observable, and we are just considering the recoverability of this shadow information. So it's not like a completely description of the quantum states in a classical way.
Okay, I see. So like maybe the classical shadows data set would be like a subset of the shadow information.
Yeah, the classical shadow, okay, like a data set.
Okay, and so that makes perfect sense. So now the point of your talk, just so that I was clear on it, is that if you have multiple channel arrangements, multiple mappings through your quantum channels, then this you're looking for channels that produce the same shadow information output, right? Because the shadow information output is classical, right?
Yes.
But I noticed that so the information that's going through the quantum channels is quantum, yes. So you're trying to preserve the classical output in the shadow information through different channel mappings.
Yes, okay. We are using quantum channels in order to preserve the classical shadow information encoded in the quantum states.
So is there any constraints on your observables? I mean, like, is it constrained to the poly matrices, or is the
No,
observables
no,
pretty flexible?
it doesn't have any constraint.
Oh, that's cool. Okay, wonderful. Thank you so much.
Okay, no problem.
Can I ask a question?
Yes, please.
Yes. So I was wondering, have you considered the measurement errors, or is the measurement error can somehow be incorporated into this quantum channel?
No, so for now the what operations we can do, we consider them to be ideal. So now we only have the states we available are the noisy quantum states, but what we can do them are just the ideal quantum operations. So that we are doing more like theoretical analysis. So for more practical cases, we could incorporate the measurement noise into the framework.
Yeah, thank you.
No problem.
Okay, on the last slide, can you maybe say a bit more about what you mean by combining with quantum error correction and mitigation?
Okay, so like in this case study, we compared the performance of our method with the conventional error mitigation method, right? So it can achieve a lower cost, and it will have a larger scope of application, as it does not require the noise to be invertible. And however, there is also some disadvantage of our method because it assumes that the noise is modeled as a single quantum channel at the end before the measurement. So maybe there are some thoughts needed to combine to make our protocol practical error mitigation one.
Okay.
Can I ask a question?
Yes, please.
Okay, I'm wondering how do you choose the combination? Oh, no, how do you decompose the retriever map D?
How do I decompose the retriever?
Yes.
Okay, so we proved that the retriever can always be decomposed into two quantum channels. And we also proved that the decomposition with two quantum channels can achieve the optimal value of gamma. So it can be decomposed. Decomposition can be calculated with the semi-definite programming. If we just write the retriever D as a combination of two quantum channels, and then the semi-definite program will optimize these two quantum channels.
So you mean that the optimal decomposition only contains two quantum channels?
Yeah, I mean that there is an optimal decomposition that contains two, but there could also be optimal decomposition that contains more quantum channels, but two is enough.
Okay, I see. So because in some cases the retriever map may contains the decomposition with negative coefficient, right?
Yes.
So usually you one of the optimal quantum channel is that one corresponding to the negative coefficient. Is it the case?
So yes, the optimal decomposition has two quantum channels, and
One of them is
one of them is the positive coefficient. One of them has the negative coefficient.
Okay, and then okay. Thank you much.
Okay, no problem.
Okay, is there any other question? If not, let's thank the speaker again. Okay, great. So let's move on to the last talk of this session. The speaker will be Koji Yamaguchi, who will tell us about beyond IID and the resource